November 11th, 1940. Camp Holabird, Maryland. The morning air carried the smell of diesel exhaust and freshly turned earth as a peculiar vehicle rumbled through the gates of the Army's automotive testing facility. Behind the wheel sat a Willys Overland engineer, his knuckles white against the steering wheel, knowing that everything rode on for the next 72 hours. The vehicle looked almost comically small next to the standard Army trucks parked nearby. At 80 inches on the wheelbase, weighing 2,400 pounds, it seemed more toy than military machine. But under that flat hood, beneath sheet metal still warm from the drive down from Toledo, beat an engine that represented 2 years of obsessive engineering, countless sleepless nights, and one man's refusal to accept the word impossible. The Army testers approached with clipboards and skepticism. They had already seen the Bantam prototype 2 months earlier. That little vehicle had impressed them with its nimbleness, but questions lingered about durability, about power, about whether such a small machine could truly meet the demands of modern mechanized warfare. Now Willys Overland, a company teetering on the edge of bankruptcy, was asking them to consider something different. What those testers couldn't know, what they couldn't see written in the specifications or measured with their instruments, was the story of how this engine came to exist. A story of a brilliant engineer who had designed 100-mile-per-hour staff cars in the First World War, who had built straight-eight engines for America's finest automobiles, now applying all that genius to transform a wheezing, oil-burning disaster into something that would help win the greatest war in human history. The crisis had begun 2 years earlier, in early 1938, when Delmar Gale Roos, known throughout the automotive world as Barney, walked through the doors of the Willys Overland plant in Toledo, Ohio, for the first time as the company's new executive vice president and chief engineer. The company that had once been America's second-largest automaker, producing hundreds of thousands of vehicles annually in the 1910s and 20s, had been reduced to a shell. The Great Depression had nearly destroyed Willys Overland. The company had filed for bankruptcy in 1933. For 3 years, it operated under federal court supervision, producing cars in small batches of a few thousand units at a time, always one misstep away from final collapse. In 1936, the company had emerged from bankruptcy, reorganized as Willys Overland Motors, Incorporated, under the leadership of Ward Canaday, a former advertising man who had taken on the role of chairman. Canaday understood marketing and finance, but the company desperately needed engineering expertise. That's why he had recruited Barney Roos. Roos arrived with an impressive pedigree. Born in the Rif, Bronx in 1888, he had attended manual training high school in Brooklyn, then studied electrical and mechanical engineering at Cornell University. At Cornell, he had distinguished himself not just academically but athletically, winning both the intercollegiate and national fencing championships. He had also gained recognition as a photographer, taking a picture of a 3-horse fire engine team that was syndicated throughout the world. After graduating from Cornell in 1911, Roos joined General Electric, working under Sanford Alexander Moss on steam turbines, gas turbines, and centrifugal compressor development. In 1913, he moved to Locomobile as assistant research engineer. During World War I, Locomobile sold trucks to the British Army, contributing more vehicles to that war than any other American company. Roos had been part of that effort. After the war, in 1919, Roos moved to Pierce Arrow as assistant to Chief Engineer David Ferguson, succeeding him as Chief Engineer in 1921. He rejoined Locomobile as Chief Engineer in 1922, where he helped design a new straight-eight engine. After a stint with Marmon in 1925, where he led development of a small straight-eight, Roos was named Chief Engineer at Studebaker in 1926. At Studebaker, Roos had overseen the relocation of the entire engineering department from Detroit to South Bend, Indiana. He had redesigned engines, developed innovative suspension systems, and collaborated on thin-wall bearing technology that revolutionized engine design. His work on independent front suspension, which he called planar suspension, had been introduced on Studebaker cars in 1935 and represented cutting-edge automotive engineering. But in 1936, Roos's personal life had fallen apart. His wife divorced him. Suffering greatly, he accepted a 1-year temporary assignment with the Rooties Group in England, which distributed Studebaker products in the United Kingdom. That sabbatical changed his perspective. In England, he became convinced that smaller cars with smaller engines made good economic sense, a radical idea for an American engineer accustomed to designing powerful luxury automobiles. When Ward Canaday offered him the position at Willys Overland in early 1938, Roos saw an opportunity. The challenge appealed to him. Willys was struggling, yes, but it was also a blank canvas. He could rebuild the company's engineering department from scratch, implement his ideas about efficient small car design, and prove that brilliance could overcome adversity. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Roos found when he arrived in Toledo was worse than he had imagined. The engineering department was demoralized, understaffed, and working with obsolete equipment. The production facilities were ancient, parts of the factory complex dating back to 1895. The company was so broke that Chairman Ward Canaday would berate engineers for wasting drafting paper. One story from this period captures the desperate atmosphere. According to company legend, during an early meeting where Canaday was criticizing engineers for minor expenses, Roos had finally had enough. The tall, athletic engineer reportedly stood up, walked over to Canaday, physically lifted the chairman, and deposited him in a nearby wastebasket to make a point about priorities. Whether the story is literally true or embellished, it reflects the tension between penny-pinching survival mode and the investment needed for engineering innovation. But the real crisis revealed itself when Roos was shown the engine that Willys was currently using in its light cars. The 4-cylinder L-head engine displaced 134 cubic inches. On paper, it produced 48 horsepower at 3,400 revolutions per minute. Those numbers sounded adequate, barely, for a small civilian automobile in the late 1930s. A Ford of the same era produced 60 horsepower. The problem wasn't the power rating, the problem was reliability. Roos ordered the engine taken to the dynamometer for testing. A dynamometer, or dyno, is a device that measures engine power output while subjecting the engine to continuous load, simulating real-world operating conditions. It's the most fundamental test of engine durability. The Willys engine failed after just 2 to 4 hours on the dyno, 2 to 4 hours. Then the engine would begin consuming excessive oil, bearings would wear out, the water pump would leak, the cylinder head would leak, the engine would shake its own starter loose. It suffered from chronic pre-ignition knock, a condition where fuel ignites before the spark plug fires, causing damaging shock waves through the engine. 4. Comparison. A reliable automotive engine of that era should run continuously on a dyno for at least 100 hours without failure. Military specifications, which Roos knew from his work during World War I, were even more demanding. The Army would expect an engine to run 150 hours under full load without significant degradation. The Willys engine couldn't run for 4 hours. Roos understood immediately that this wasn't just a problem. This was an existential crisis. Everything in an automobile depends on the engine. The greatest suspension system, the most efficient transmission, the most innovative body design, all of it means nothing if the engine is unreliable. He gathered his small engineering team and laid out the challenge. They needed to take this fundamentally flawed engine and transform it into something durable, reliable, and powerful enough to meet whatever demands the future might bring. He gave them a target that seemed impossible given where they were, starting. Develop an engine that produces 65 horsepower at 4,400 revolutions per minute and runs for 150 hours on the dyno without failure. That target represented a 35% increase in power output at a higher engine speed, combined with a reliability improvement of at least 37-fold. They had to achieve this while keeping costs manageable, because Willys Overland couldn't afford expensive exotic materials or complex manufacturing processes. Roos began by analyzing every aspect of the existing engine design, identifying each weakness, each point of failure, each compromise that had led to its poor performance. The approach he took was methodical and uncompromising. Every component would be examined, every design decision would be questioned. Nothing would be accepted simply because that's how it had always been done. The engine block itself was cast iron, which was appropriate. Cast iron was inexpensive, easy to manufacture, and provided good wear characteristics. The bore and stroke dimensions were reasonable for the displacement. The basic architecture didn't need to change, but almost everything else did. The crankshaft was the engine's fundamental weakness. The crankshaft converts the up and down motion of the pistons into rotational motion that drives the wheels. In the original Willys engine, the crankshaft was poorly balanced. As it spun at high speeds, the imbalance created vibrations that propagated through the entire engine, causing premature wear on bearings, loosening fasteners, and creating stress fractures. Roos designed a fully counterbalanced crankshaft. Counterbalancing means adding precisely calculated weights opposite the throws of the crankshaft to cancel out the forces created by the reciprocating masses. This is complex engineering. The calculations must account for the weight of the pistons, connecting rods, and the crankshaft itself. The counterweights must be positioned and sized exactly right, or they make the vibration worse rather than better. The new crankshaft transformed the engine's character. Where the old engine had shaken and rattled at high revolutions, the new design ran smoothly. This smooth operation meant less stress on every bearing, every seal, every bolt. It meant the engine could run at higher speeds for longer periods without wearing itself to pieces. The pistons presented another challenge. The original engine used cast iron pistons, which were heavy. Heavy pistons mean more reciprocating mass, which means more stress on the crankshaft, connecting rods, and bearings. It also limits how fast the engine can safely rev. Roos specified aluminum pistons. Aluminum weighs about 1/3 as much as iron, so aluminum pistons dramatically reduce reciprocating mass. This allowed higher engine speeds and reduced stress on all the moving parts. Aluminum also conducts heat better than iron, helping keep combustion temperatures under control. But aluminum pistons required careful engineering. Aluminum expands more than iron when heated, so the pistons had to be designed with the right clearances to prevent seizing when the engine reached operating temperature. The piston rings, which seal the combustion chamber and control oil, had to be redesigned to work with the aluminum material. The bearing system needed a complete overhaul. The original engine used antiquated bearing technology that wore quickly under load. Roos and his team implemented insert bearings, a technology that had been developed for aircraft engines and was just beginning to appear in advanced automotive applications. Insert bearings consist of a steel backing coated with a thin layer of softer bearing material, like bronze or lead tin alloy. The thin layer of soft material conforms to the shaft, provides excellent lubrication characteristics, and can be manufactured to very tight tolerances. When properly designed, insert bearings last far longer than the older technology and can handle higher loads. This was the same thin wall bearing technology that Roos had helped develop during his time at Studebaker, working with the Cleveland Graphite Bronze Company. He was now applying that advanced knowledge to transform the Willys engine. The lubrication system received extensive redesign. Oil is the lifeblood of any engine. It must reach every bearing, every moving surface, in the right quantity, at the right pressure, at the right temperature. The original Willys engine's lubrication system was inadequate, leading to oil starvation under hard use and contributing to the rapid bearing wear. Roos designed a new oil pump, new oil passages within the engine block, and a new pressure relief system. The new lubrication system ensured that even under the most demanding conditions, every critical surface received adequate oil flow. The valve train, which controls the opening and closing of the intake and exhaust valves, needed refinement. The original design had excessive friction and poor valve timing. Roos redesigned the camshaft profile, optimized the valve springs, and improved the rocker arm geometry. These changes improved breathing efficiency, allowing the engine to produce more power while running more smoothly. The flywheel, which stores rotational energy and smooths out power pulses from the firing cylinders, was far too heavy. The original flywheel weighed 57 pounds. Roos reduced it to 31 pounds through careful analysis of what was actually needed. This weight reduction meant the engine could accelerate more quickly and respond better to throttle inputs. Every change was tested, measured, and validated. The engineering team worked long hours, often through the night, iterating on designs, manufacturing prototype parts, testing them on the dyno, analyzing the results, and going back to the drawing board when results didn't meet targets. The atmosphere in the engineering department transformed. The demoralization that Roos had found when he arrived gave way to excitement. The engineers realized they were doing something significant. They weren't just fixing a broken engine, they were creating something that could compete with anything else in its class. Months passed. The work continued through the summer of 1938, into the fall, through the winter. By early 1939, the new engine was ready for serious testing. The first extended dyno run exceeded everyone's expectations. The engine ran for over 100 hours at full load without significant problems. Power output had increased to over 60 horsepower, oil consumption was minimal, no leaks developed. The starter stayed attached. The pre-ignition knock was gone. Roos had achieved his goal. The engine that had failed after 4 hours now ran for 100 hours. The engine that produced 48 horsepower now produced over 60. The transformation was complete. The engine needed a name. Someone on the engineering team suggested Go Devil, capturing the spirit of what they had created. The name stuck. The Go Devil engine would make its debut in some of the 1939 Willys cars, rated at 61 horsepower at 3,600 revolutions per minute. But Roos had designed this engine with more than civilian cars in mind. His experience during World War I, his time in England hearing Hitler speak at the Berlin Motor Show in 1937, his understanding of world events, all of it told him that America would soon need military vehicles. He had heard rumors through industry contacts that the Army was interested in a light vehicle. Various manufacturers had submitted experimental designs over the years. Marmon Herrington had presented four-wheel drive Fords. Bantam had contributed Austin-derived roadsters. The Army itself had built an experimental machine gun carrier called the Howie Wiley, nicknamed the Belly Flopper. Nothing had fully satisfied the Army's requirements. But Roos sensed the need was becoming urgent. War had broken out in Europe in September 1939. France had fallen in June 1940. The British were fighting alone against Nazi Germany. America was still neutral, but everyone understood that neutrality couldn't last. Then, in July 1940, everything changed. On July 11th, the United States War Department sent a letter to 135 automotive and equipment manufacturers. The letter outlined specifications for a new vehicle the Army desperately needed, a lightweight, four-wheel drive reconnaissance vehicle that could carry 3 men and their equipment across any terrain. The specifications were precise and demanding. The vehicle must have 4-wheel drive with a 2-speed transfer case. It must have 3 bucket seats. The windshield must fold down. It must have blackout and driving lights. It must weigh no more than 1,300 pounds with a payload capacity of 600 pounds. The wheelbase must be no longer than 75 inches. The maximum height, with the top collapsed, must be 36 inches. The engine and drivetrain must be capable of smooth operation at speeds ranging from 3 to 50 miles per hour. The deadlines were shocking. Manufacturers had 11 days to submit bids. The winning bidder would have 49 days to deliver a working prototype, 75 days to complete 70 pre-production vehicles. Of the 135 manufacturers contacted, only 2 submitted bids: American Bantam Company in Butler, Pennsylvania, and Willys Overland in Toledo, Ohio. Bantam had been working with the Army on preliminary designs and had influenced the specifications. Their chief engineer, Harold Christ, immediately engaged freelance designer Carl Probst from Detroit. Probst produced initial designs in just 2 days, worked up cost estimates the next day, and Bantam submitted their bid complete, with detailed blueprints on July 22nd. Willys Overland didn't have blueprints ready. The bid they submitted was based on cost and time analysis. They were the lower bidder on price, but they couldn't commit to delivering a prototype in 49 days. They needed more time. The Army awarded the initial contract to Bantam, but the Army also had doubts about whether the small Bantam company could handle large-scale production. So they did something unusual. They provided Bantam's prototype plans to Willys and Ford, inviting them to develop their own versions. This decision infuriated Bantam. But the Army argued that since they had paid for the development, they could share the information with whomever they chose. The Army needed vehicles desperately and couldn't risk relying on a single, small manufacturer that might not be able to scale production. Barney Roos looked at the Bantam design and immediately recognized both its potential and its weakness. The Bantam prototype used a Continental engine because Bantam didn't manufacture engines. The Continental produced 45 horsepower with 86 foot-pounds of torque, just barely meeting the Army's requirements. Roos knew the Go Devil engine was superior. It produced more power. It was more durable. It had been thoroughly tested. Most importantly, Willys manufactured it in-house, which meant they could scale production without depending on outside suppliers. He also knew the Army's weight limit was impossible. 1,300 pounds was absurdly low for a vehicle that had to be strong enough to cross rough terrain while carrying 3 men, weapons, ammunition, and supplies. Physics and materials science put a lower limit on how light you could make a functional military vehicle. Roos made a strategic decision. He would exceed the weight limit but deliver superior performance. He would show the Army that the Go Devil engine, combined with robust construction, would produce a vehicle that could do everything the Army needed, even if it weighed more than the original specification called for. The engineering team went to work designing the Willys prototype. They used the same Spicer four-wheel drive components that Bantam was using, proven parts from an established manufacturer. But they built everything else around the Go Devil engine. The deadline was brutal. November 11th, 1940. That's when the Willys prototype, internally designated the Quad, had to arrive at Camp Holabird for testing. The team worked around the clock. Engineers, machinists, welders, assemblers, everyone understood what was at stake. If Willys won this contract, it could save the company. The military would need thousands of these vehicles, tens of thousands, maybe more. Those production numbers represented survival. As the deadline approached, the prototype took shape. It was compact, rugged, purposeful. The flat hood allowed engine access from the front. The body was rectangular, maximizing interior space within the dimensional constraints. The seating placed the driver on the left, a passenger on the right, and a fold-down jump seat in the rear. November 11th arrived. The Willys Quad was loaded onto a trailer and driven to Camp Holabird, Maryland. It arrived on schedule. The Army began testing immediately. All 3 prototypes, the Bantam, the Willys, and a newly submitted Ford design, were evaluated side by side over the next 2 months. The testers drove them over rough terrain, through mud, up steep grades. They measured acceleration, top speed, fuel consumption. They evaluated visibility, ease of operation, and maintenance access. They loaded them with equipment and personnel. They ran them hard, looking for weaknesses. The Willys Quad stood out immediately. The Go Devil engine's superior power was obvious. The Willys had better acceleration. It could climb steeper grades. It had more torque for pulling through difficult terrain. The engine ran smoothly and reliably throughout the testing. But there was one problem. The Willys prototype weighed 2,423 pounds, far over the specified limit of 1,300 pounds. The Army had already discovered through testing the Bantam prototype that 1,300 pounds was unrealistic. Bantam's prototype weighed 1,840 pounds. Ford's weighed slightly more. The Army had quietly raised the acceptable weight limit for the next round of testing, but Willys was still significantly heavier than the others. If Roos wanted to win the contract, he had to reduce weight dramatically while maintaining the performance advantage provided by the Go Devil engine. The ordeal of reducing weight began in late November 1940. Every component was stripped from the prototype and studied. Could it be made lighter? Could it be eliminated entirely? Could a lighter material be substituted? First, all unnecessarily long bolts were shortened. This sounds trivial, but 1/4 inch of unnecessary length on 50 bolts adds up to pounds. Every bolt in the vehicle was examined. Hundreds of bolts were shortened. Then the engineers reduced the thickness of the steel used in the body and fenders. This required careful analysis. Make the steel too thin, and it would be too weak, would dent too easily, would fail under stress. But every unnecessary thousandth of an inch represented weight that could be saved. Reinforcing plates were examined and reduced where possible. Some were eliminated entirely after stress analysis showed they weren't needed. Tough alloys were substituted in the frame for heavier carbon steel. Aluminum and magnesium would have been ideal for weight reduction, but both materials were in short supply and prioritized for aircraft production. The engineers even analyzed the paint. How many coats were actually necessary? How thick did each coat need to be? Could they use a lighter weight paint formulation? Through careful testing, they eliminated nearly 10 pounds of paint without compromising corrosion protection. The fuel tank was redesigned and relocated. The spare tyre mounting was optimized. The seats were made lighter. The windshield frame was thinned slightly. Door hinges were redesigned. Pound by pound, ounce by ounce, the weight came down. The process took weeks. Every change had to be documented, analyzed for strength implications, tested. Nothing could be weakened to the point of failure. The vehicle still had to be durable enough for military service. When the slenderized prototype was finally assembled, it weighed 2,164 pounds, still over the original specification, but 259 pounds lighter than the first prototype. More importantly, the weight was now comparable to the Ford and Bantam designs, while the Go Devil engine still provided superior performance. In March 1941, the Army issued the next round of contracts. Bantam would produce 1,500 Model 40 BRC vehicles. Ford would build 1,500 modified GPs. Willys would build 1,500 of their MA model, an improved version of the quad. All three designs would undergo further testing and evaluation throughout the spring and early summer of 1941. The Army needed to make a final decision soon. War was coming. Everyone could sense it. The testing reports came in from units across the country. Infantry units evaluated the vehicles for reconnaissance. Artillery units tested them as gun tractors. Quartermaster units assessed them for logistics support. The Infantry Board's report was representative. After extensive field trials comparing all three designs, they concluded that the Willys' performance was superior in acceleration, maximum speed, grade climbing, and cross-country capability. The Go Devil engine's power advantage translated directly into better performance in the field. The Quartermaster Corps Technical Committee, responsible for procurement decisions, reviewed all the test data. On January 22, 1941, they issued a recommendation. The Jeep design should be standardized across all manufacturers based on the Willys chassis and the Go Devil engine, but incorporating the best features from the Bantam and Ford designs as well. The Ford GP had introduced innovations in the front sheet metal design, including a piano hinge hood that provided excellent engine access. That feature would be adopted. The Bantam had demonstrated excellent suspension and brake design. Those elements would be incorporated, but the fundamental vehicle would be Willys. The Go Devil engine had won. On July 15, 1941, Willys Overland signed a contract with the United States War Department to begin production of what would be designated the Willys MB. The MB designation indicated it was a military model, the B referring to the second design iteration after the MA. Production began in November 1941. Within weeks, Japan attacked Pearl Harbor on December 7th, and America was at war. The demand for Jeeps became insatiable. The Army needed them for North Africa, for the Pacific Islands, for training bases across America, for Lend-Lease deliveries to Britain and the Soviet Union. Willys ramped up production as fast as possible, but by October 1941, it became clear that even at maximum capacity, Willys alone couldn't meet demand. Ford was brought in to build Jeeps under license. Ford's designation would be GPW. The G indicated a government contract. The P designated an 80-inch wheelbase. The W meant it was built from a Willys design. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The production statistics ultimately reached staggering levels. By the end of World War II in August 1945, the combined output from Willys and Ford totaled 647,870 military jeeps. Willys produced 362,841 units. Ford produced 280,448. American Bantam, which had originally won the prototype contract, produced 2,675 before production was shifted to Willys and Ford. The Go Devil engine powered every single one of those jeeps. 647,870 engines, all based on the design that Barney Roos had developed from that failing Willys four-cylinder. The Jeep became legendary. General George Patton called it one of the weapons that won the war. General Dwight Eisenhower said that America could not have won World War II without it. Soviet Marshal Georgy Zhukov, commanding Red Army forces, credited the Jeep with enabling Soviet mobility during crucial offensives. The vehicle appeared on every front. In North Africa, Jeeps carried supplies across the desert. British Special Air Service commandos mounted machine guns on Jeeps and conducted lightning raids behind German lines. In the Pacific, Marines drove Jeeps across volcanic sand on Iwo Jima. In Europe, Jeeps spearheaded advances through France and into Germany. The Go Devil engine proved its worth under conditions that would have destroyed lesser designs. Jeeps operated in the Sahara Desert, where temperatures exceeded 120 degrees Fahrenheit. They operated in Russia, where temperatures dropped below -40 degrees. They forded rivers, climbed mountains, and crossed jungles. The engine's reliability became legendary. Field maintenance was straightforward. The simple design meant that even minimally trained soldiers could perform basic repairs. Parts were interchangeable. If one engine failed, parts could be scavenged from another damaged vehicle to get a third vehicle running. The durability that Roos had built into the design, by transforming that failing 4-hour engine into something that could run 100 hours on the dyno, translated into real-world reliability that soldiers depended on. The counterbalanced crankshaft meant the engine could run at high speeds for hours without shaking itself apart. The aluminum pistons and insert bearings meant it could handle the high loads of climbing steep grades or pulling heavy loads. The improved lubrication system meant it wouldn't fail even when operated in extreme conditions. Production continued after the war ended. During the Korean War, Jeeps remained the standard light vehicle. The Go Devil engine continued powering military Jeeps until 1952, but the engine's life extended far beyond military use. In 1945, Willys introduced civilian versions of the Jeep. The CJ2A, for civilian Jeep, used the same Go Devil engine. Farmers bought them for work around their farms. Utility companies used them for rural service calls. Hunters and outdoor enthusiasts discovered their capability. The Go Devil engine powered civilian four-wheel drive Jeeps from 1945 through 1954. It was used in DJ two-wheel drive delivery Jeeps through 1964. Jeep station wagons and trucks used the engine through the mid-1950s. The engine was also sold for commercial, marine, and generator applications. The long-term success of the Go Devil engine went far beyond what even Barney Roos envisioned when he began redesigning it in 1938. An engine that started as an unreliable 48-horsepower disaster that failed after 4 hours ultimately powered vehicles for more than 2 decades. In applications ranging from desert warfare to suburban mail delivery, Roos himself continued working for Willys after the war. For the Jeep station wagon, Willys' first passenger car after World War II, he developed a version of the planar independent suspension he had created at Studebaker years earlier. The wagon, marketed with what Willys called planar-dyne suspension, became the first Willys product with independent suspension. Kaiser Motors acquired Willys in 1953. Roos retired shortly after, but continued consulting for Willys until his official retirement in 1958. On February 12, 1960, Roos was returning by train from a meeting in Reading, Pennsylvania, to his home in Bronxville, New York, when he fell ill. He disembarked at Philadelphia and was admitted to Temple University Hospital. He died there the next day at age 71. At the time of his death, He held 18 patents, most for automotive innovations. He had received an honorary Doctor of Law degree from Creighton University in 1943, recognition from an institution that must have meant something to a man who had built a distinguished career despite never completing formal engineering training beyond Cornell. The obituaries noted his work on the Jeep, but Roos never sought celebrity. He was an engineer's engineer, a problem solver who cared about the work itself rather than public recognition. Those who knew him remembered a tall, handsome man who was a brilliant conversationalist on art, drama, economics, politics, and science. A man who had won fencing championships and taken photographs that were syndicated worldwide. A man of diverse interests and capabilities who chose to apply his genius to automotive engineering. The story of how Barney Roos transformed a failing engine into the heart of the Jeep resonates on multiple levels. It's a story about engineering excellence, about understanding that reliability comes from meticulous attention to every detail. The counterbalanced crankshaft, the aluminum pistons, the insert bearings, the improved lubrication. Each of these changes addressed a specific weakness. Together, they transformed the engine's fundamental character. It's a story about the relationship between innovation and necessity. Willys Overland was desperate. The company needed the military contract to survive. That desperation created urgency that cut through bureaucracy and forced bold decisions. When the Army's weight specifications proved impossible, Roos didn't abandon the project. He bet everything on performance, calculating correctly that superior capability would overcome the weight penalty. It's a story about institutional resilience, a company that had gone through bankruptcy, that operated under federal court supervision for 3 years, that had been reduced to producing cars in tiny batches, somehow found the resources and the will to compete for and win one of the most important military contracts in American history. It's a story about timing. Roos arrived at Willys in early 1938 and immediately began transforming that inadequate engine. He completed the work in 1939. The Army issued its specifications for a light military vehicle in July 1940. When that request arrived, Willys had an engine ready that was superior to anything competitors could offer. Without those 2 years of preparation, Willys couldn't have competed. The broader implications extend beyond one company or one engine. American victory in World War II depended on industrial capacity. The United States produced staggering quantities of weapons, vehicles, ships, aircraft, ammunition, and supplies. That production capacity overwhelmed the Axis powers. But capacity alone wasn't sufficient. The products had to work. They had to be reliable. They had to be repairable in the field. They had to perform under conditions ranging from Arctic cold to tropical heat. The Go Devil engine exemplified the American approach. It wasn't the most sophisticated engine design. German engineers could have critiqued aspects of it, but it was robust, reliable, manufacturable at scale, and effective under real-world conditions. Those characteristics mattered more than engineering, elegance. The Jeep itself embodied this philosophy. It was simple, rugged, and functional. It could be mass-produced quickly. It could be maintained by soldiers with basic mechanical knowledge. It could operate anywhere. Those attributes made it more valuable than more complex alternatives. The decision to standardize the design across multiple manufacturers demonstrated industrial sophistication. Rather than having 3 different vehicles with incompatible parts, the Army mandated standardization. This meant parts from a Willys Jeep could be used in a Ford Jeep. This meant mechanics trained on one vehicle could work on any vehicle. This meant the logistics of supplying spare parts became manageable. Germany never achieved this level of industrial rationalization. German forces used dozens of different vehicle types with incompatible parts and different maintenance requirements. This complexity strained their logistics system and reduced overall effectiveness. The numbers tell the story. 647,870 American Jeeps. Germany produced only about 16,000 Volkswagen Kübelwagens, their roughly equivalent vehicle. The production disparity of 40-1 reflected the fundamental industrial advantage that decided the war. Behind those production numbers stood people like Barney Roos, engineers who solved problems, workers who manufactured components, managers who organized production. All of them contributed to victory through their specific expertise and dedication. The transformation of that failing engine represents something profound about problem solving. Roos didn't invent any radically new technology. Counterbalanced crankshafts existed. Aluminum pistons existed. Insert bearings existed. Improved lubrication systems existed. What Roos did was apply known technologies systematically, addressing every weakness, optimizing every component, testing thoroughly, and iterating until the engine met his demanding standards. That systematic approach, that refusal to accept inadequate performance, that willingness to keep working until the problem was solved, that's what transformed failure into excellence. The lesson extends far beyond engines. How many projects fail not because the necessary knowledge doesn't exist, but because the systematic effort to apply that knowledge isn't made? How many problems persist not because they're insoluble, but because no one invests the time and effort to solve them properly? Roos had 2 years to transform the Willys engine before the Army's specifications arrived. He used that time well. He didn't wait for a crisis to begin. He saw the inadequacy and addressed it immediately. When the crisis came, Willys was ready. That preparation made the difference. American Bantam won the initial prototype contract and influenced the specifications. But Bantam didn't manufacture engines and couldn't scale production. Ford joined late and could have built Jeeps around any engine. Willys won because they had the superior engine ready to go, developed by an engineer who understood that reliability comes from exhaustive attention to detail. The Go Devil engine, running smoothly under the hood of that prototype at Camp Holabird in November 1940, carried within it 2 years of meticulous engineering work. The Army testers measured horsepower and torque. They clocked acceleration times and maximum speeds. They evaluated grade climbing and cross-country performance. But what they were really evaluating was Barney Roos's refusal to accept failure, his insistence on excellence, his systematic approach to problem-solving, his understanding that every component matters, that every detail contributes to overall performance, that reliability comes from addressing every weakness rather than papering over problems with hopes and excuses. 647,870 Jeeps, each one powered by an engine that descended directly from that work. Each one carried soldiers into combat, carrying supplies to frontline units, carrying wounded to field hospitals, carrying messages between commanders, carrying the tools and equipment that supported military operations across 3 continents. The mathematics of war are written in many forms: strategic planning, tactical innovation, cryptographic breakthroughs, scientific advances, industrial production. All of them matter. But sometimes victory comes down to whether an engine runs for 4 hours or 400 hours, whether it produces 48 horsepower or 60, whether it fails under load or keeps running when soldiers depend on it. Barney Roos ensured that when soldiers turned the key in a Jeep, the Go Devil engine would start. When they pressed the accelerator, the Jeep would move. That when they drove it through mud, across deserts, over mountains, through jungles, the engine would keep running. That reliability, built into the design through systematic engineering excellence, represented a form of power that no amount of propaganda or ideology could overcome. It was the power of things that work, of designs that solve real problems, of engineering that addresses human needs rather than pursuing abstract perfection. The legacy persists. Every modern Jeep traces its lineage back to that World War II MB with the Go Devil engine. The current Jeep Wrangler still features the distinctive 7-slot grille that originated with the wartime design. It still has removable doors and a fold-down windshield, echoes of features designed for military necessity. The Jeep brand has become synonymous with rugged capability and go-anywhere attitude. That reputation was earned on battlefields across the world, powered by an engine that one determined engineer transformed from an embarrassing failure into a war-winning success. When visitors to automotive museums today stand before a restored World War II Jeep, They're looking at more than a vehicle. They're looking at the physical manifestation of systematic problem solving. Every component tells a story. The counterbalanced crankshaft reducing vibrations, the aluminum pistons reducing weight, the insert bearings improving durability, the enhanced lubrication system ensuring reliability. They're looking at what happens when someone refuses to accept failure, when someone systematically addresses every weakness, when someone tests thoroughly and iterates until success is achieved. They're looking at proof that one engineer, starting with a fundamentally flawed design, can through skill and determination create something that helps change history. The Go Devil engine didn't win World War II by itself, but it powered the vehicles that gave Allied forces mobility. It enabled reconnaissance, it supported logistics, it provided the foundation for tactical flexibility that complemented strategic planning and operational execution. And it all started with Barney Roos looking at an engine that failed after 4 hours and deciding that wasn't good enough. With him gathering his small engineering team and setting a goal that seemed impossible. With him systematically addressing every weakness until that impossible goal became reality. The wartime production numbers of 647,870 Jeeps represent individual stories. Soldiers who drove those Jeeps through combat, medics who used them to evacuate wounded, supply sergeants who kept units equipped, commanders who directed operations from Jeep-mounted radios, chaplains who brought comfort to troops in the field, engineers who cleared mines and obstacles, each person depending on the vehicle to perform, depending on the engine to run, depending on the work that Barney Roos had done years earlier in a struggling factory in Toledo, Ohio. The legacy of that work extends beyond the individuals. It extends to strategy, the Allied strategy of mobility, of mechanized warfare, of projecting power across vast distances. All of it required reliable vehicles. The Jeep became the foundation of that mobility. It extends to industrial philosophy, the American approach of mass production, of standardization, of designing for manufacturability and maintainability. All of it was demonstrated in the Jeep program. Those lessons influenced how America manufactured everything from trucks to tanks to aircraft. It extends to organizational resilience. Willys Overland emerged from bankruptcy and within a few years became a crucial defense contractor. That transformation showed that with the right leadership, the right engineering talent, and the right circumstances, companies could recover from seemingly fatal setbacks. The story reminds us that innovation doesn't always mean invention. Sometimes innovation means taking existing technologies and applying them more effectively than anyone has before. Sometimes it means systematic problem-solving rather than revolutionary breakthroughs. It reminds us that preparation matters. When opportunity arrives, success goes to those who are ready. Roos didn't wait for the Army contract before developing the Go Devil engine. He saw the need and did the work. When the opportunity came, Willys was ready to compete. It reminds us that details matter. Every unnecessary pound of weight removed from the Jeep prototype mattered. Every improvement to the crankshaft balance mattered. Every enhancement to the lubrication system mattered. Excellence emerges from attention to thousands of small details, not from one dramatic gesture. The Go Devil engine, that most American of power plants, simple, robust, reliable, powerful enough for the task, represented the democratic ideal applied to engineering. It wasn't built to be elegant. It was built to work. It wasn't designed to impress other engineers. It was designed to serve soldiers. It didn't pursue technological sophistication for its own sake. It pursued effectiveness. That practical focus, that emphasis on what works rather than what's theoretically optimal, that willingness to use known technologies effectively rather than demanding breakthrough innovations, that characterized American industrial success during World War II. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.